As far as I know, you have been studying, you have been doing the chapter 3 of Patria's book, okay? And today we will do the paragraph 3.9, okay? So we will do the statistics of paramagnetism. So paramagnetism. Okay, so first of all, what is paramagnetism? What is paramagnetism? Paramagnetism is one kind of reaction that a material or a substance has to an applied magnetic field. Okay. So if you are not too specific, every substance has some reaction to an applied magnetic field. Okay. So for example, you might be familiar with the more macroscopic effect of ferromagnetism. If you apply a magnetic field, you see that the system magnetizes in a given direction, which means that as a magnetic dipole induced, and this creates more magnetic field. Okay? There are many other kinds of reaction to magnetism, and ferromagnetism is the more common and is the more macroscopic, because paramagnetism is also very common. It's actually much more common than ferromagnetism, but its effects are so tiny sometimes, very tiny sometimes, and you need precision measurements to be measured. Okay, and in fact, the first ones to study in a quantitative way paramagnetism were the first people were at the end of the 1800s, beginning of the 1900s. In particular, Pierre Curie, that you know was the husband of the couple Pierre and Marie Curie, and he did his PhD in studying the effects of magnetism, and therefore we will talk about, for example, Curie's law, and that was discovered by him, and it's the effect of temperature on the paramagnetic properties of a material. Okay, so since we are doing statistical mechanics, we have to have a microscopic model from which we want to extract macroscopic information. Okay, the microscopic model of ferromagnetism, for example, it's a bit complicated. I'm not sure, have you seen something with Matteo on this? Not yet. Not yet. You will later on. But the microscopic model of paramagnetism is very simple. It's just you assume that your n atoms are completely independent, okay, like in an ideal gas, and each of them has a magnetic moment mu. So there is a magnetic moment mu, and as you know from classical electromagnetism, what happens if you have a magnetic moment mu and a magnetic field H directed in a direction which is not parallel to mu? What happens to the magnetic moment? Okay, so if there is dissipation, if we're talking about ideal particles and magnetic moments, what happens? You were saying something. Okay, if you don't have dissipation, what's the energy of energy of a magnetic moment? Minus mu dot h. Okay, we are considering that. The energy is conserved, right? So it cannot align if there is no dissipation. If the system is completely isolated, so what happens? Hmm? No, there is only one particle. One particle. I'm talking about the simplest case of one particle with magnetic dipole moment in a magnetic field. Mm-hmm.
Maybe the particle tries to minimize the energy.
No, the energy is conserved.
So nothing will happen.
Nothing. It stays like this. No. Something happens. What does it do? You're doing like this. It starts rotating in such a way, because that's the only motion that it can do, such that this thing is a constant. Right? It can move on a circle in such a way that the projection is constant, and therefore this product is constant. So if there is no dissipation, the magnetic moment just turns around. Okay. If there is dissipation, this turning around, so dissipation means that there is some other degrees of freedom. For example, the particle can radiate some photons, okay, or by colliding with another particle in a similar situation can exchange energy, and then this particle can go on and exchange energy with the walls. So if you're talking about thermodynamics, we have systems which are confined and interacting with the environment, with the boxes and so on and so forth. So if there is dissipation, so mu dot is mu cross h if there is no dissipation. If there is dissipation, what happens is that, as you were saying before, the particle tries to minimize the energy, right? Because it loses energy, and therefore tries to minimize the energy. Where is the minimum of the energy here? Is when mu is parallel and in the same direction of the magnetic field. Okay? So, because in this case, this becomes minus mu h. Okay, otherwise it's minus mu h cosine of theta, where theta is this angle here. Okay? Since I have n independent atoms, the total energy of my system is going to be the sum of the energies of the various independent particles. Okay. Now let's assume for the moment that this angle here is completely free. Okay, so the particle can choose to adjust this angle as it wishes. So the partition function of the n particles will be the sum over all these angles of all the particles of e to the minus beta e. Okay, so this sum, as usual, means the sum over theta 1, theta 2, theta 3, blah, blah, blah. But since this is a continuous variable, it's going to be an integral then in the end. So, okay, so since these are independent particles and the energy is the sum of various terms, this becomes the product of various terms. Okay, in particular, it becomes the product becomes the nth power of the partition function of the single particle. Okay. So now we have to do this sum. Okay, so this sum, the sum over theta, since we are in 3 dimensions, should be equal to the integral over the solid angle. Okay, we can normalize it by the total value of the solid angle, which is 4 pi. So what's the omega? How many angles do we actually have to consider in 3 dimensions? 3 angles. No.
In general, but not to find.
2 dimensions, 1 angle. 3 dimensions, 2 angles. Okay. I'm not talking about a rigid body. The rotation along this axis here is irrelevant. Okay. So 2 angles. Let's say theta and phi. What's the solid angle differential expressed in terms of theta and phi? D phi, and then sine theta d theta. Okay. Okay, very good. So this sum here becomes integral d phi. Phi goes from 0 to 2 pi. Theta goes from 0 to pi. And then we have this integral here. E to the, no, I left it like this. E to the beta h mu cosine of theta. Okay, now, this is equal to 1/2. Okay? Because it's 2 pi over 4 pi. And now we have to do this integral here. Any ideas how to do this integral? Substitution? Speak up.
Let u be cos theta or cos constants. Cos theta.
No, I can't hear. Say.
By using substitution.
Uh-huh.
So let u be beta h cos theta. Du will be d sin theta.
Okay. So let's actually just take cos theta. Okay. So your friend is saying, let's define the new variable u, which is cos theta. Okay. Then du will be minus sine theta d theta. Okay. And the minus is important because the integral, if in this variable, goes from 1 to -1. So the minus means that the integral goes from -1 to 1. Okay. So -1 to 1 du e to the beta mu h u. Okay, so this integral is easy to do. It's just the integral of the exponential. So it's okay. So let's define this as q1 to the n. And therefore q1 will be equal to hyperbolic sine of beta mu h divided by beta mu h. Okay. Now, we want to find the average so the thing which is interesting is the component. Okay, so this gives us the partition function. Using the partition function, we can calculate many things. Okay, in particular, we can calculate average values. That's why we introduced the partition function to calculate. It's a trick to calculate averages. Okay, so we want to calculate the average. So first of all, let's put the other axis. Let's say that h is directed along the z-axis, and then we have our other two axes. This is the x-axis, this is the y-axis. I want to calculate the average of the mu is a vector. Okay? And the magnetization of the system is essentially n times the magnetic moment of a single atom. So let's assume that I want to calculate. So if I want mx will be n mu x. Okay. I want the average of mu x. Can you see what is this value? It's 0. Why it's 0? Because it looks symmetric. Okay. And also you have to keep in mind what's the microscopic picture that we said before. What is the macroscopic picture? Microscopic picture, sorry. That the particle rotates around the h-axis. Okay. So if it rotates in a circle, then mu x is going to be equal to mu y is going to be equal to 0. Okay. So the only thing that we can calculate is mu z. Okay. So this is consistent with the picture that I said before. And also comes from the calculation here. So for example, how would you calculate mu x? So the average of mu x, so first of all, mu x is mu sine theta this is phi, cos phi. So you have to take, so the average of mu x will be equal to sum d phi d theta sin theta of mu sin theta cos phi e to the beta h mu cos theta divided by q1. Divided by q1. Okay? So what's this integral here? This is a double integral. Okay? It's an integral in d phi and d theta. Which one would you do first? D phi. Anyone wants to do d theta first? Why would you do d phi first? Because the integral of cos phi is between 0 and 2 pi is 0. So you see suddenly that this thing is 0. You don't have to do the integral in d theta. You could do the integral in d theta. You would have something which is non-zero. Okay. And then you have to do the integral in d phi, you find 0. So you save one integral by doing. Okay, so this is 0. Now, this is a confirmation of what we said before. So what we expect on symmetry ground, on microscopic picture, and so on and so forth. But as always, if you have a picture, and you know your calculation has to confirm that picture. Okay. Otherwise, there's something wrong with the theory. Mu z is similar thing. Let me erase this so I have a little bit more space. Okay, let me also erase this since I have the result over there. We have d phi, d theta, sine theta, divided by 4 pi. And now we have to put mu cos theta. Okay? Without phi dependence. Now the integral in d phi is easy and gives just 1/2. We get 1/2 integral. We do the change of variable that our friend suggested to us before. -1 to 1 du u e to the beta mu h u. Okay? There is a mu here. So I let you do this integral. It's very simple. It's again the integral of how do you do the integrals of powers times exponential? How do you do it? Which technique do you use? Integration by parts, right? And so integration by parts is integral of in dx of u v prime is equal to uv minus integral dx So which one is the u and which one is the v prime in this expression? U is u and okay, very good. So then you have to take derivatives of the exponential, which are still exponential, so you don't do anything. All right. So if you do this integral, you end up with the following expression. And then you divide it by this expression here. Mu hyperbolic cotangent of beta mu h minus 1 divided by beta mu h. Okay? This thing is called the Langevin function. Mu times the Langevin function of beta mu h. Okay. Now we have an expression, and we can go and look. Okay. All right. So let's go here. So let's call this thing so let's see, let's plot the magnetization as a function of the temperature, okay? Or nu z, just to remove factors of n. First of all, on general grounds, okay, on physical intuition, what do you expect this curve to do? If I increase the temperature, the magnetization should go up or should go down? Suppose there is a value of the magnetization here, this temperature. Okay? This, I don't know, 20 Celsius. I increase the temperature. What do you expect? The magnetization goes up or goes down? What do you think? Should go down. Why? Speak up, speak up. Exactly, because the particles will have more kinetic. In this case, it will be thermal energy in some sense. So the magnetic field is less relevant, right? Because we have two scales of energy in this problem. Okay, one is mu times h. It's some joules or electron volt or something. Okay, and what's the other one? kBt. Okay, and in fact, look, our function is function of the only dimensionless parameter that we can build in this model, which is mu h divided by kBt. Beta is 1 over kBt. Okay? So if this energy is much smaller than this energy, it means that thermal fluctuations will let the particle go like this, irrespective of the position of the magnetic field. On the other hand, you can think that you are essentially turning off the magnetic field, because its energy scale is irrelevant with respect to the other energy scale of the system. So this should go down. And that's correct. In fact, L of x, so large temperatures means small x. And if you plot the Langevin function as a function of x, it has this property that grows from x equals 0, which is infinite temperature, up. Okay? If I take very, very small temperatures, what should happen to the magnetization? Will be stronger, but arbitrarily strong, or will, if I look at the mu z, will it saturate at a certain point, or we tend to an asymptote given by
1 over beta h. Okay. If we look the expression for small temperature, the term which is dominant is 1 over beta mu h.
But small temperature is large or small beta?
Larger beta.
Okay, so for larger beta, this term you say is dominant.
Yeah.
No.
No, it's 0.
This goes to 0.
Yeah,
Okay. And the cotangent, the hyperbolic cotangent goes to 1. Because it's the ratio of the cosine with the sine. And they both grow like the same exponential, so it goes to 1. So asymptotically, you can neglect this second term here, which is important instead for small temperature, because the cotangent has a divergence for small temperature, for a small x, okay? Because it's 1 over the tangent. The tangent goes to 0, and the cotangent goes to infinity. So the cotangent has a divergence, which is cancelled by this term here. But for large beta, which is small temperature, that term is negligible, the cotangent goes to 1. So the Langevin function goes to 1. Asymptotically, never touches 1. Okay? And this thing here, okay, goes to mu. In fact, what happens for very small temperature? That the system has very small thermal fluctuations, and so it goes to the ground state. And the ground state, we say that is when mu is completely parallel and in the same direction of h. So mu z is equal to mu. Okay? So this is the plot for the Langevin function. It's the same because it's a function of of mu h divided by kBt. So it's either large fixed h and large temperature, or small temperature, or fix the temperature and change the magnetic field. You get the same picture because the function is a function of the ratio. Okay? It's always like this. When you solve a problem in physics, in the end, you are left with the function which is, in particular, if you have not simple powers, but you have more complicated functions, a function which is a ratio of, so it's only a function of dimensionless variables. And therefore, if you have only two scales of energy or, I don't know, or whatever it can be, two forces, two homogeneous quantities, they have to appear in a ratio in the solution. Okay. So when you change one, the change of one and the other are not independent in some sense. You can change the ratio by changing either one or the other. If you fix the ratio, you have the same property. Okay. So L of x for small x has this expansion, x over 3 minus x cubed divided by 45 plus, so actually orders of x to the fifth. So if we put back the definition of x, we find that the magnetization is mu times mu times 1/3 mu h divided by kBt plus orders x cubed. So one thing that you can measure in the lab is the magnetic susceptibility. The magnetic susceptibility, like all the susceptibilities, essentially tells you how the system reacts to turning on a magnetic field. Okay? So it's the derivative of the magnetization that you can measure in the lab, when the experimentalist turns on the knob that turns on the magnetic field. So in this case, if you don't have magnetic field, the magnetization is 0. Okay, along the z, because the system is completely isotropic. So the particles will go all possible directions in a uniform way. You take the average of any vector, you get 0. But now you turn on a little bit of magnetic field, and you get a little bit of superposition of your particles feel the magnetic field and decide to go along the direction of the magnetic field a little bit. So the susceptibility measures this. It's the derivative of the magnetization in the z direction, because it's the only direction. H, when h goes to 0. Okay? So in this case, you will have, so since the magnetization is n times that thing there, you will have n mu 0 squared divided by 3 kBt. Okay. Mu squared, I mean the absolute value of the vector. This thing here is called Curie's law. And tells you that the reaction of the system at a given temperature is at the small with respect to a small magnetic field is smaller the larger the temperature. Okay. And the coefficient, this is given more or less. You have, the density of your gas, for example, or your piece of paramagnet, and and this is a microscopic quantity. Okay. So okay. So let's go. Do you have questions? So I think you are starting doing now calculation in statistical mechanics in which you have to calculate these partition functions and so on and so forth. This is one of the simplest cases. So it should be clear to you how to do this. So if you have any questions, just ask me if something is not clear. And we can. Okay. So again, the system is composed of n independent particles. Therefore, the partition function becomes the nth power of the partition function of a single particle. And from the partition function of a single particle, we can calculate averages of quantities. Okay? For example, if we calculated the average of mu x, it came out to be 0, and we understood this from symmetry principles. We calculated mu z, and this turned out not to be 0, but inversely proportional to the temperature for large temperatures. Okay? And this is quite generic, and it's called this inverse proportionality to the temperature is called Curie's law. Okay. Okay, let's now consider what happens. So this, needless to say, I mean, this description is entirely classical, right? But it cannot be correct because essentially we know that magnetic moments and angular moments in microscopic particles are behave in a completely different way than classical particles. For example, the angular momentum is quantized. It's quantized strongly, okay, in the sense, like also the momentum of a particle in a box is quantized. But if the box is large, the various values of the momentum are very close together. So usually classical mechanics is a quite good approximation. For magnetic moments, for angular momentum, this is not the case because the quantization is pretty big. So the angular momentum of a chair, it's quantized, but you don't notice it because it's so big that the difference in angular momentum, h bar, does not really make much of a difference. But if you are talking about an electron, or if you are talking about atoms or molecules, that counts a lot. Okay? So we should take in account the full quantum mechanical description. So the magnetic moment is proportional to the angular momentum of a particle. Okay? If you actually write this as G E h bar divided by mc, and you write this in units of h bar, where h bar is Planck's constant divided by 2 pi, okay? Then this is dimensionless, this is dimensionless, and this is called Bohr's magneton. So if we think about if we think about, so L is quantized, then L squared is equal to j plus 1, h bar squared. Okay, where j is an integer or semi-integer, depending on whether the particle is a fermion or a Bose. And whether we're talking about, whether this is, if it is the angular momentum, orbital angular momentum can only be an integer. If it is spin, and that part also counts in the magnetic moment, then it can be half integer. So, and then we have this quantity here, which measures, so if the particle was point-like, really point-like, had no structure, in classical mechanics, we would expect this G to be 1. Okay? So for something like the electron, you go and for a particle like the electron, classical mechanics, but even quantum mechanics without relativity, will predict that G is equal to 1. Then you go in the lab and you measure, and you find that G for the electron is equal to 2. Okay? Actually, minus 2 is in the opposite direction of the spin. But never mind. So G for the electron is equal to 2.00231930436622 plus or minus 1.5 times 10 to the minus 12. This is experimental error. So why did I write down this number? Because this is probably the most accurate measurement that has ever been done in the history of physics. Okay, there are maybe another couple of examples. It's like you measure something, this is a pure number. Okay, I didn't write any units of measure because this is a pure number. So first of all, all the digits here are very important. In particular, the difference between 2 and this thing here is quite important, because this is the famous G minus 2 problem that people had to face in the 40s. In the 40s and the 50s, and let people understand how quantum electrodynamics really works. Okay, because these corrections are quantum corrections. If you take the electron is described by, so the electron is a spin 1/2 particle and is described by which equation? Dirac's equation. Okay, you take Dirac's equation, you calculate G, and you find 2. 2.00000. It has to be 2. Okay? So Dirac's equation cannot explain the rest of these digits. And the experimental error is really, really small. So the experimental error is on these digits here. So this has to be explained by something else. And in fact, explaining this made people understand how quantum field theory really needs to be done. Okay, because if you calculate naively these kind of quantities in quantum field theory, you find 2 plus infinity. Okay, so you find divergences everywhere. So understanding how to take care of these divergences in a precise way, in a quantitative way, not just to say there is a correction, I don't know how to calculate the correction. No, you really want to calculate the correction and have it matched with the experimental results. Then you understand how your theory works, how the mathematics should be handled. So for the electrons, this is minus 2. So just to say that this number is just a number in our calculations, but it's quite important. okay, because it tells you a lot about both the physics at very high energy scale, actually. Inside the electron, you are probing the structure, not inside the electron, that's not correct, because the electron is a point-like particle, okay? So you are probing very close to the core of the electron, to energies which are, if you go and see, you know, in order to go to these digits, you need to go to energies which are of the order of 130 GeV, which is an energy scale which is quite common these days. Why? Because of the Higgs, right? So measuring these things, you are probing physics of the electron at energies which are comparable to the mass of the Higgs. Moreover, more surprises. So go and look at the G of the proton. What do you expect? The same, with the plus. You know what you get? You get the plus. That's the thing. But you get 5.6. Okay. This tells you that the approximation of a proton being a point-like particle is not good at all. Okay. The proton is not a point-like particle for what concerns magnetic moment. Right. In fact, if you go also the neutron has a magnetic moment, and -3. So actually understanding these numbers here, it's interesting because you have to understand how the quarks behave inside the nucleon. Right? Okay. So the proton is made of 2 up quarks and 1 down quark. The 2 up quarks have charge 2/3, and the down quark has charge -1/3. The neutron is made of 1 up and 2 down quarks. And understanding how these things interact in the nucleus, in the nucleon, in the proton or the neutron, gives you these numbers. So, so making precision experiments at a macroscopic level can tell you a lot about the physics at microscopic level. Okay. So, mu square is G square, Bohr's magneton, and then we square L, and we get J plus 1. Mu Z is quantized G, Bohr's magneton times M, and M can go from -J to J in step of 1. So for example, if J is 1/2, M is -1/2 of 1/2. If J is 1, we get -1, 0, 1, and so on. So let's erase this. And let's, okay, so independent particles. So again, the partition function becomes the power of, the nth power of the single particle partition function. We calculate the single particle partition function. And now we have to sum over all the m's Okay. Well, x is equal to b beta g j times h. Okay. So how do we perform this sum? What's this sum called? It's a geometric sum. Very good. So it's a geometric sum, so we use the geometric sum theorem. It says that sum for n that goes from 0 to capital N of y to the n is 1 minus y to the capital N plus 1 divided by 1 minus 1. Okay. Here it goes from minus j to j. So what do? You take out, you change variables in some sense. You write m plus j is equal to n, let's say. And then you take out, you multiply here by a factor. Yeah. So this gives the result e to the minus x, e to the 2j plus 1 divided by j, x minus 1. Okay, which you can also write as a hyperbolic sine of 1 divided by 2j x, hyperbolic sine of x divided by 2j. Okay, so I followed actually the convention that it's on the book. In my opinion, it would have been better to normalize this in this way. As you know, if I put a constant in front of the partition function, this doesn't change anything. Okay, just a constant that does not depend on the temperature, on the magnetic field, and so on and so forth. I would have write this as this. Okay. Why? Because let me tell you. Let's multiply this by this constant. Okay. So, how would you take the classical limit of this expression? So suppose classical mechanics is a limit of quantum mechanics, right? So we should find the previous results by taking a suitable limit of. So what of the quantum? Think about the chair. Okay, so the angular momentum of the chair is quantized, but we said that it doesn't matter because it's big. Okay. So what will be the quantum limit here? The classical limit, sorry, of this quantum expression. J goes to infinity, and we need to keep something constant, right? J goes to infinity, and why x is constant? Look at x. Contains j inside, right? So if you want to map... J goes to infinity, but mu b times j is constant, and it's equal to mu. Because the Bohr's magneton is very small. Okay? So if we want a magnetic moment which is a classical magnetic moment, so it's sort of large. So mu b times j is mu, is a constant, and then we take j to infinity, which means simply that j is large, I don't know, like 10, 20. Okay, that theoretically. So if we do that, what do we get? That x becomes b, g, actually let's put g also in the game, okay? G mu b j is equal to mu. Okay. So we have x is b beta mu h. And here, what do we have? So here, 1 over 2j disappears. And we get x. And here, what do we have to do? How do we take the limit of 2j plus 1 times sine, hyperbolic sine of x divided by 2j? We expand the hyperbolic sine, and the first term is just x over 2j. Okay, so x over 2j, and then the correction is of order 1 over j cube. And so 2j plus 1 multiplied by x over 2j just becomes x. And this is the result that we found before. Right? So this is just to say that when you have a quantum expression, two things can happen. There can be a new phenomenon that disappears when you go to the classical limit. Okay? But if not, for example, if the magnetization has a limit when you take the classical limit, it has to correspond to the classical. Okay, so let's calculate the average of mu z in this, for this expression here. So the average of mu z yes.
We do not introduce the
Then for the partition function is not an observable, right? It's not something you can measure. So the partition function will not have a limit. Okay, will go to infinity. But if you take the averages, average quantities with the partition function, they go to the same values. In fact, now we can see in the. So if you are smart and you normalize your partition function in such a way that it has a limit when you send some parameters to infinity and so on and so forth, with constants, because I mean this constant here does not change. When I take the average values, it's taking derivatives of the log of the partition function, right? When I take log, the constant, they become additive constants, and when I take derivative, the derivative of a constant is 0. So this thing is completely irrelevant for the physics, and it gives the mathematics the right. Here, yes, exactly. That's the idea. In fact, essentially, the idea is the following. You have a sum over m, okay, and of 1 divided by 2j plus 1, and m goes from minus j to j. This is essentially, when j goes to infinity, this becomes the integral of dm. Okay? 1 over 2j plus 1 is dm, and this becomes an integral between minus 1 and 1. Divided by 2, actually, because. And if you remember, this is like this is cosine of theta. This is the variable u. And 1/2 came from the integral d phi divided by 4 pi. So it's the same thing. So yeah, I can write this as in this way, this means whatever function I put here, I should put the same function here. In fact, if I put the identity here, 1, then this sum is 1, and also this integral is 1, because it's 4 pi over pi. But if you want to do things, now since I have done these calculations many, many times, I know where it's going to go, so I can, adjust. But if you don't, the best thing to do is to look, not to look at the partition value, but look at observables, like average values of things. So sometimes you see, when you study mathematics, then there is some theorem that, for example, you want to prove, when you take limits or something like that, you say, for every epsilon larger than 0, there is a delta. And sometimes in the proof you find, in the theorem you find, for every epsilon larger than 0, there is a delta equal epsilon times 57 divided by 32. And you say, why did you put 57 divided by 32? Because then it simplifies things in the end. But you can only do it if you have already done the proof before. So it's a bit cheating. Right? So and here it's the same. Since I know where I want to go, I can put this constant, which does not change anything. So, but let's do the calculation. So there are two ways to do the calculations. First of all, mu z is sum over m minus j to j of mu times m, and then this thing here, b. Oh, sorry, let's write it this. mx divided by j, divided by the partition function q1. Okay? Or you can write it as 1 over beta d by dh logarithm of the partition function. The magnetization along the z direction is equal to n times mu z, average mu z, and you find that this is n times g b mu j bj of x, where the function bj is called the Brillouin function. Okay, here you see now what I meant by you have to look at average values, because the limit here is now straightforward, without considering constants or not constants in Q1. The limit here, we define this to be mu. X is a function of mu, so x stays put, and when you send j to infinity, this becomes 1, this becomes 1. And here we have to take the limit in the same way as our friend was suggesting before, by expanding the cotangent. First term in the cotangent is 1 over the argument. This cancels the 2j. Okay? And we end up with 1 over x. And this is exactly the same expression before. But for finite j, the expression is different. And for finite j, the expression is different. So let's plot for reference. So this is the Langevin function. Okay, that we plotted before. The Brillouin function looks like this for the smallest j possible, which is 0. But if I have 0, then I don't have magnetic moment, right? If you don't have neither spin nor orbital, so 0, I will just give 0. Okay, it's impossible to magnetize. So what's the next smallest one that we can get? 1/2. Exactly. Very good. So j is equal to 1/2. And then you increase j. And this asymptotically tends point by point uniformly to the Langevin function. Okay. Just one simplification because it comes out a lot. If j is equal to 1/2, then this expression here simplifies, and you find that the average mu z is mu hyperbolic tangent of x. Mu b, sorry. Okay, so I will stop here a little bit early because I have to do some exams in 10 minutes. So if you have any questions. No questions? As always, I suggest that you go through the calculations by yourself. Tom?